well-known Baire category theorem. As a prelude to that, we introduce the concept of knower dense sets. Now recall that earlier we had discussed everywhere dense sets, and now we are introducing the concept of knower dense sets. So what exactly is a knower dense set? So let us define it first. So we start with a metric space X, which we assume, because for this purpose it is not necessary, but we can assume if you want this to be complete. But for the time being, that X is a metric space or a topological space, because this definition holds in both a metric space as well as a more general class of topological space. So X a metric or topological let A be a subset of so definition. A is said to be knower dense right here. Said to be knower dense in X if given any non-empty open set U, we can find a non-empty open set V such that V is contained in U and V intersection A. So this is any non-empty open set U we can find a non-empty open set V. V is contained in U and V intersection A is T. Okay, let us look at this concept. Now for that, we look at some examples. Let us take X to be equal to R and A to be a line then A is so let us look at this. This is R2. This is your X. Now suppose there is a line. Even we, I mean, some curve, one-dimensional curve would work. So let A be given by this line. Now what we can say is that suppose you take an open set. In some open set, U then what you can say is that there exists an open subset of U, namely of V, a open subset V of U. This is again open, such that V intersection A is empty. That is, V has no intersection with A. It's a very typical example. Now, I'll give an example where that is not true. Then A is lower dense. We take another example. Okay. Now, what it says is that for any open set U, there should be a open subset V whose intersection with the given set is empty. Let us look at another example. So we take X to be equal to R. Let A be equal to the set of all rationals. Is Q now what is the structure of open sets in R? So let V be a then it contains elements of Q. Contains elements of Q, because in any open set in R contains both rational points and irrational points. Okay. So every non-empty open set in R rational and irrational. which implies one cannot find an open set such that U intersection Q empty. One cannot find open sets because no, sorry. So this is an example of a set which is nowhere else. Another example. Suppose you take the following sets. Let x be equal to r. Let a be equal to the unit disk the line so let me write A as, so if you choose this set, then your A is the following. Equal to the set union the set xy now you see that this is what? This is R2, this is equal to your x. So here we choose x equal to R. Now this is the one that you are talking about. This is the unit disk. I have taken the open disk. You can also take the closed disk. And the line. So this is the set A. This is the unit disk. And I will just avoid the boundary. This is the unit open disk. Okay. And the line x equal. That's is A now what you have is you choose. What does it say? It says that see if this nowhere dense if for every open set U you can find an open subset V such that V intersection A is empty. Okay. So we show that this is not possible. Consider the open set. That is the open unit disk. Okay. Every subset of non-empty intersection with A. Therefore, A is not lower dense. That is, it is somewhere it is dense. Okay. The negation of lower dense is somewhere it is dense. Note that the negation of ഞാൻ അങ്ങോട്ട് എത്തിക്കാം. The negation of lower dense is that somewhere it is dense. Not Therefore, that makes it amply clear what the negation of knower dense. These examples give you an insight into the concept. Now let us look at more examples, or what you call knower dense sets. Now a fourth example is, now these are some simple examples. The set of all integers is knower that's clear. It is also knower dense in Q. Okay. Now another example is Q. This we have looked at. This is in fact everywhere more sophisticated examples are as follows. In fact, this example has been considered already. That is, what we are saying is that the x-axis in R2 is knower dense. So the next example is, if V or if A is a proper subspace Rn, not just a subspace, it's a proper subspace of Rn, then it is knower dense. Let V be a normed linear space. Then of course it's a topological space. In fact, it's a metric space. Let A be a proper closed of X. then A is a knower see the fact is the following. See, if, for example, I can demonstrate it with R2. You take R2 and suppose you take a one-dimensional subspace of that, it's a line passing through the origin. You see that when you take an open set, it is an open set in R2, not on this. So you see that if you take a segment of this, it is not an open set. When whatever you call an open set is something like this. That's why there is a lot of gap. Okay, so you can find another open subset of that which has no intersection. So it's the same case. So when you take a normally linear space, now you take a proper subspace of that, closed subspace of that, say call it A, then you see that you take an open set in the normally linear space. It becomes it's something like this. Okay, I mean no subset of the proper subspace can become an open set. That's the point. No subset of the proper subspace can become an open set. That's the point that you have. Okay. So this is knower dense in. Let us look at another example. Consider the set. So you take R. Now A you take as this sequence 1 by n n belonging n is a natural number union the zero element. To see that the sequence 1 by n converges to 0. Now you can easily see that this is why it is an overdone set. See, the situation can go wrong only at the point 0, because 0 is the place where there is a crowding around of the points 1 by n, the sequences 1 by n. So it's 1, 1 by 2, one by n. So you have a sequence of points. Now you see that to take any open set. See, this is the place where you have to, there is enough gap between elements of this where you can have an open set in the space. Now, which contains no point from the given set. Now, you see that even if you take a open set containing 0, still you can find a open interval which does not contain any of these elements. For instance, you have say then 1 by n and 1 by n plus 1. Look at this interval. This is an open set. This does not contain any of these elements from this set. Okay, therefore this is knower dense. in spite of the fact that the sequence converges to 0. Okay. So these are all examples of that. Now what we try to do is we go for a characterization of lower than 6. A characterization of lower than 6. Okay. So we will okay. A subset, let X be a and A contained in X is nowhere dense in X, which we have already defined. If and only if the interior of a quotient is a necessary and sufficient condition. Okay, we say that A is nowhere dense if and only if the interior, this is the interior, that is the interior of that's the statement. Okay, so let us prove this here. Now you can check this in all the examples that we have considered. Okay, so first step is verify this statement. On the examples, lower denses we have considered as examples. Now I'll just take one example. We have seen that For example, R now you see that Z closure is equal to Z itself. Okay. Therefore, Z closure interior is equal to empty. Go through, look at the definition of the interior and the closure. Okay. On the other hand, consider containing. And you see that Q closure is equal to all of R because Q is dense in R. What about Q closure interior? This is equal to R interior is equal to R. On the other hand, consider Q contained in R, which is given. So these are some verifications that you do. Now let us prove this here. Let's provide a proof of this. Assume so we are now proving this. Assume claim dense in the sense of the definition that we have given earlier. So let us apply this. So A closure interior is empty, which implies every X belonging to A closure is not an integer. Not an integer. Every X belonging to A closure is not an integer. Which implies for every R positive, B, the ball the open ball with radius r for any r is not contained in equation. That means there are some points in B which is not there in equation. Not contained. Okay, and what does that mean? That implies there exists y belonging to, for any r there is a y corresponding y, such that y does not belong to equation. Which implies what? Y is not a limit point of a. What does it mean? This implies there exists a delta positive such that is contained in EXR and by delta intersection A is empty, and which implies just apply the definition with U as B XR and V as By delta. Then this implies A is so that proves one part of it. Now what we want to prove is this forward direction. So we assume A is what we claim is that a closure interior now what one does is we use contrapositive. So just briefly recall, suppose you want to prove P implies Q. A property implies this. So this is what we are doing. So this is the property P, this is the property Q. Then it is enough to prove that not Q implies not P. Okay, so that is equivalent to proving a property Q if and only if not so we use this argument. So this is the basis of our argument. Therefore, let us assume this. So now we assume a closure interior is non-empty. That's all this. Then there exists X belonging to interior, which implies there exists R positive such that BXR is contained in a closure, which implies every Y belonging to is a limit point of A. What does this mean? This implies P Y delta intersection A is non-empty for every delta. That means all balls of radius delta has a non-empty intersection with A. Okay, and that implies the negation of the definition of lower density. That implies A is not lower density. So the interpretation is that consequently by the contrapositive arguments that we have said, if A is that combination. Okay, that's a nice place to stop. So we have now a characterization of the so-called lower densities. Now what we want to state and prove the next time is the Baire category theorem, which is a fundamental result as far as the complete metric spaces are full sets. So thank you very much. We meet next time.